Okay, let's take a look at changes of state. And changes of state, of course, refer to changing a solid into a liquid or a liquid into a gas into a liquid into a solid, vice versa. So when we talk about the states of matter, we're talking about solid, liquid, and gas. And when it comes to changes of states, there's kind of two directions we can go. We can go in a direction where our substance is absorbing heat, and we call that an endothermic process. So if we think about something like melting, right? If we melt ice, well, the ice must absorb heat in order to go from a solid to a liquid. Furthermore, if you take water in the liquid phase or any liquid and you convert it into a gas, right? It takes heat to evaporate or to boil the water. And so going from a liquid to a gas or evaporation would also be considered an endothermic process. Also, if you were to go from a solid to a gas directly, that's called sublimation, and that would also be an endothermic process. You see that with something like dry ice. Now, on the other hand, if we go in the other direction, we call those exothermic processes, ones that liberate heat. So if we go from a gas down to a liquid, right? Condensation, you can see here it says heat energy is liberated, okay? And so if you think about if you've ever had the misfortune of reaching across a kettle or a pot of boiling water or something, and you reach across and your arm goes in the steam, well, it creates a very severe burn. Why is it? It's because the steam is a lot hotter than your body temperature. And so as soon as the steam hits your skin, it cools down immediately, but it releases a lot of heat along the way as it goes from a gas to a liquid. And so that's how steam burns occur. And then also, if we go from a liquid down to a solid, if we freeze something, where's my yellow pen? There we go. Again, heat energy is going to be liberated along the way. So we see here endothermic and exothermic changes of state. So if we go from a more organized structure like a solid, then to a liquid, and then from a liquid to a gas, that would be an endothermic process, right? Heat is going in. And conversely, if you go from a more disorganized phase like a gas and go down to a liquid, or if you take something like a liquid and freeze it, that would be an exothermic process, one that liberates heat. Okay, classify the following processes as endothermic or exothermic. So let's start with A. If ice chips melt at room temperature. So if you have an ice chip that's nothing more than water in the solid phase, and then if it's melting, okay, you're converting it into water in the liquid phase. So you're taking ice and you're melting it. That means it's absorbing heat, and so that would be an endothermic process. Endothermic process. And with B, it says water from the air condenses on the exterior of a cool glass. And I'm sure everybody's seen that before. You have water from the air, which is water in the gaseous phase, and then it gets converted into a liquid on the side of your glass of cold juice, so that it gets converted to water in the liquid phase. And so in that case, you're going from a more disordered substance, water vapor, into liquid water, which is more organized, and so heat is going to be released, and so that would be exothermic. Right, now condensation, I've already spoken about this already, but you need to know that condensation is when we have a gas and it gets converted into a liquid. And again, you should also know that that is an exothermic process. So we saw that in the previous example. If you take water vapor and it condenses into liquid water on the side of a cold glass, that's one example. And I told you another example is if you've ever been burned by steam before, okay? That is also, an exothermic process that releases a lot of heat. All right, vapor pressure. So vapor pressure, I remember this is something that wasn't covered in my high school chemistry class, but my children aren't old enough to be in this class, but they do have a bit of an idea of what vapor pressure is because I use it all the time. I'll talk about vapor pressure and I'll explain that in just a second. So let's go back to the idea of evaporation or vaporization, trying to mix the two words together. So evaporation or vaporization is an endothermic process where we have a liquid that's being converted into a gas, right? So if you have a glass of water that's open, right? Imagine you have a glass of water, right? It's not a very good glass of water, but anyhow, if you have a glass of water and it's just open to the air, right? Eventually, the glass is going to be empty. Why? Because all the liquid water is going to evaporate, okay, over time. Now, when the water evaporates at sea level, we would say that it's evaporating at standard atmosphere. So if you've ever heard of standard pressure or standard atmosphere before, it says here it's the pressure needed to support a 760 millimeter column of mercury in a barometer tube. Sometimes you'll see this called, so we'll say here standard atmosphere, I'll just abbreviate it here, as 760 millimeters of Hg, because Hg is the elemental symbol for mercury. And there's some interesting history about that, where a scientist by the name of Evangelista Torricelli did the initial experiment in Italy, where he determined that at sea level, the column of mercury was 760 rather millimeters of mercury high. But that really standard atmosphere, when you see this 760 millimeters of mercury, that's the atmospheric pressure at sea level. Okay. Now I live in Colorado Springs, and Colorado Springs is not at sea level, right? It's a mile above sea level. And so atmospheric pressure here is lower, but again, that's not standard atmosphere, right? Standard atmosphere is where it's at sea level. I'll write it in here again. Okay. So, oops. Sea level is standard atmosphere. Now, a torr, it says here a torr, which is named after Evangelista Torricelli, is the pressure needed to support a 1 millimeter column of mercury in a barometer tube. So that's where where the definition of a torr comes from. So check this out. If you take and you have some water in a container, okay, let's say you have a glass of water and then you put a cover on the top of it. Well, initially, what's going to happen is that the water is going to start to evaporate. And you see that right here. You see these little, this is supposed to represent particles of water in the vapor phase, okay? And then after some time, you're going to see that the level of the water is going to go down because more of the molecules of water are going to go from the liquid phase into the gaseous phase, but then eventually, after enough time, the water level is going to get to a certain height and it's not going to go any higher than that. Why? Because there's going to be an equilibrium established between the water in the liquid phase and the water in the gaseous phase. And you see this arrow that I'm drawing down here. This is an arrow that represents equilibrium. Okay. Equilibrium is represented by this arrow. If you try to draw the arrow like this, that is not an equilibrium arrow. That's called a resonance arrow, which we don't worry about right now. So that would be an equilibrium. So you see here that when it reaches equilibrium, that the water vapor here is going to have a certain pressure, right? Where the particles of water vapor are going to be colliding with the lid, they're going to be colliding with the sides of the container. That is vapor pressure. Okay, that is vapor pressure, is that amount of pressure that vapor is pushing with against the walls of the container. Now, now I'm just talking about water right now, but what if you have something like gasoline? Okay, let's say you spill some water. Let's say you spilled a glass of water and you spilled a glass of gasoline on your floor. Now, I don't recommend doing either, but anyhow, which one's going to evaporate faster? Well, the answer is gasoline is going to evaporate much faster. And so it's going to be pushing against the atmosphere harder than water would, right? It's going to evaporate faster. And so we say that substances that evaporate faster have higher vapor pressures. And so where I use this in my everyday life is just as a joke with my children. I'll say, "What happened to the Apple TV remote?" And they'll say, "I don't know." And then I'll say, "It must have a very high vapor pressure because it just seems to evaporate. It's just poof, it's gone." Maybe you would say, "Oh, the money in my bank account has a high vapor pressure, right? It just disappears very quickly." Anyhow, maybe that's not funny. And so here are some tables that show some vapor pressures of some liquids and some trends as well. So first trend we want to notice is that vapor pressure decreases with molecular weight, and consequently London dispersion forces increase. So check this out. Let's say we compare these three compounds right here, pentane, hexane, and heptane. You'll notice that with these three compounds, as you go from pentane to hexane to heptane, and we're going to learn about the structure of these compounds later on in this class. You see as their molar mass increases, their molecular weight goes up, okay, that their vapor pressure decreases, right? The vapor pressure decreases, or you could say the lowest molecular weight compound has the higher vapor pressure. And why would that be? It's because the lowest molecular weight compound here is going to have the weakest London forces, whereas the bigger one is going to have the stronger London forces. And so it's London forces that are preventing the molecules from separating from one another as we go from a liquid to a gas. Now, the reason I'm comparing pentane, hexane, and heptane is because they're all nonpolar compounds. But what if we compare butanol and pentane? So if I just compare pentane and butanol, you'll notice that the vapor pressure of pentane is much, much higher than the vapor pressure of butanol, even though they have molar masses that are almost identical of around 73 atomic mass units. So why is it that the vapor pressure of pentane would be so much higher? It's because butanol can participate in what? Hydrogen bonding, right? Because it has this OH here, and so it can hydrogen bond, whereas there's no oxygen inside of pentane, so it definitely can't hydrogen bond. Okay. And then you see that this other trend here with ethanol, propanol, and butanol, all three of those compounds are capable of hydrogen bonding, but you see that the ethanol has the highest vapor pressure, okay, and the butanol has the lowest pressure. Why would that be? Because you see that as the molar mass increases, you see the vapor pressure drops, right? The vapor pressure is highest for the smallest compound. Why? Because it has the least number of London forces. You can also see the relationship between vapor pressure and temperature, right? This is just the vapor pressure of water at specific various temperatures, okay? And you see that what happens here is that if we increase the temperature, what's going to happen? We increase the vapor pressure, right? Think about it. If you have a glass of water at 0 degrees Celsius, it's going to evaporate much slower than if you were to have a pot of water at 80 degrees Celsius or a glass of water at 80 degrees Celsius, right? The hotter it is, the faster it's going to evaporate. Why? Because it has a higher vapor pressure. You'll also notice that the vapor pressure of water is 760. Oh, wow, at 100 degrees Celsius. Well, that's where a normal boiling point or a standard boiling point comes from. Boiling point is actually defined as the temperature at which the vapor pressure is equal to the atmospheric pressure. And so that is why water boils at 100 degrees Celsius at sea level, right? But what happens to the point of water as you go to a higher altitude where the vapor pressure is lower? Well, if the vapor pressure is lower, then the boiling point should be lower. And that's why water in Colorado Springs boils at a lower temperature than it would in, say, Miami Beach. Okay, and with those thoughts in mind, let's see if we can answer this question. It says, which of these is going to have a higher vapor pressure, methanol or propanol? We can see that both of these compounds are capable of hydrogen bonding. Okay, these are both alcohols, is what we would call them. They're not the alcohol found in an alcoholic beverage. That would be ethanol. But either way, both of these compounds can participate in hydrogen bonding. But which one's going to have a higher vapor pressure? It's going to be the one with the lowest lowest atomic mass or lowest molecular molecular mass. Okay, and obviously this compound, the methanol, is smaller than the one propanol. So the answer is going to be the methanol, since less London forces, right? They both have hydrogen bonding, but since the methanol is a smaller molecule, its London forces are going to be less, and therefore it's going to evaporate faster, right? It's going to have a higher vapor pressure. All right, this is a really great illustration shown here in Figure 5.31, which just demonstrates what I was talking about earlier on. I said the definition of boiling point a couple slides ago is the temperature at which vapor pressure is equal to atmospheric pressure. So vapor pressure is equal to atmospheric pressure. Now notice it says prevailing atmospheric pressure because we know that atmospheric pressure changes depending on where we are in the world, right? If you're in New York, well, New York is pretty much at sea level. So if you try to boil water in New York, it's going to boil at 100 degrees Celsius. But if you go up to Denver, the mile high city, right, you're at a higher elevation. And so the atmospheric pressure is going to be lower. And so what does that mean? The boiling point is going to be lower. Then you go up to something like Mount Whitney, and the boiling point is going to be even lower, 85 degrees Celsius. If you go up to, something like Everest, I don't remember exactly, but I think the boiling point of water on the top of Mount Everest is like 70 degrees or something like that. So I think it would take, I don't know, an hour or something to hard boil an egg. It would take a long time to boil an egg or cook pasta or something. The sublimation and deposition, I already mentioned sublimation earlier. This is when a solid goes directly to a gas. But students oftentimes haven't heard of deposition. That's when we go from a gas to a solid directly. The most common example of deposition that you might know in your everyday life would be the forming of frost. Right? If you form frost outside on the grass and you're walking on a cold morning and you see frost, well, it doesn't mean it rained the night before. It just means it got so cold so quickly that the water vapor in the air just crystallized on the blades of grass or whatever. And sublimation, an example of that would be something like dry ice, which is just solid carbon dioxide and it goes directly into carbon dioxide in the gaseous phase. So again, going back to our ideas of endothermic, exothermic, sublimation is going to be an endothermic process because we're going from something which is more ordered, a solid, to a gas, something that is less disordered, or more disordered, less ordered, I should have said. Then we have deposition, which is the exact opposite. It's going to be an exothermic process because we're going from something that's more disordered to something that's more ordered. And then finally, melting point. I don't think I discussed melting point a whole lot yet. So melting point is just the temperature at which a solid changes into a liquid. So if we have a solid that changes into a liquid, and the solid and the liquid have the same vapor pressure. So higher melting points exist when stronger intermolecular forces are present and vice versa. Right? If you compare, something like sugar. Sugar is a solid, okay, versus, I don't know, something like butter. Butter's a solid too, okay? They're both solids, but sugar has a higher melting point than butter. Why? It must mean that the intermolecular forces in sugar are stronger than those in butter, and that's absolutely true. All right, next question is about boiling point. Which of these has a higher boiling point, THF or water? So THF is this compound here. THF is kind of a long name, but it stands for tetrahydrofuran. I don't think you need to know that, but anyhow, THF and water. And you can see that they even illustrated both of the dipoles in THF and water. So THF is a polar compound and water is a polar compound. So that means that both of these compounds, they both have London forces, check. They both have dipole-dipole forces, don't they? Right? Because they both have a dipole, okay? But what about hydrogen bonding? Can both of these, if you have a pure sample of both of these, each of these compounds individually, can they both participate in hydrogen bonding? And the answer is no. Only water can because it's the only one that has an oxygen hydrogen bond. Sure, THF has an oxygen in it, but it's not bound to hydrogen, it's bound to carbon. And so the answer is in order for us to have, or since hydrogen bonding is one of the strongest intermolecular forces, it's the strongest thing you could have with either of these compounds because there's no ions here. The answer is going to be the water. Water is going to have a higher boiling point, right? Water boils at around 100 degrees Celsius, and THF has a boiling point that's lower than 80 degrees Celsius. By the way, THF, tetrahydrofuran, it's a very common solvent in organic chemistry. There's a lot of reactions in organic chemistry that cannot be done in water, and oftentimes tetrahydrofuran, THF, is a popular choice.